Okay, hello everyone. I will tell you about imperative functional programs that explain their work. So let's say you've written a program that takes a list of integers and it pairs each integer with a string that tells us whether that integer is positive or not. You run the program, you get the result, and you realize that the result is incorrect because your program claims that 0 is a positive number. So now you're left with the task of finding bug in your program. And one way you can approach the problem is using a debugger. That is, you run your program, and by inspecting program state after each instruction, you're trying to spot the moment where program's behavior differs from your expectations. And the downside of this approach is that if you don't have any idea where the code might be located, where the bug might be located in the code, you might have to inspect huge amounts of code that are completely correct and irrelevant to producing your bug. And so it would be nice if there was some way of narrowing down the scope of search that we have to perform. And luckily, there already exists a technique that allows to do that. It's known as slicing. And in slicing, you say which parts of program's output you want explained. And as a result, you get information which parts of the program's source code contributed to computing that value. So in the example that I have given you, the incorrect value is the positive string. And so we replace all the other sub-values in the result with something that we call holes and denote them as boxes on the slide. The meaning of a hole is, I don't care how this value was produced, don't explain it. And this forms our slicing criterion, or more generally speaking, every value that contains holes will be called a partial value. And we will now be, based on that value, we will be constructing source code fragment that contributed to computing it. And since we're going from result of computations to the source code, we will call this backward slicing. And the result is our original source code with irrelevant fragments replaced by holes, meaning that they didn't contribute to producing the values we care about. And we still have to inspect some code, but now the amount of code we have to look at is hopefully smaller. And you might be wondering, how do we manage to reconstruct the program's source code from the value? And the answer is we use traces. That is, during program's execution, we record what happens at runtime. So for example, if you have a conditional instruction, then trace records which branch was actually taken when we ran the program. And we might also want to take our partial program and run it. And this process will be called forward slicing. And some more terminology. So the result of forward slicing will be known as the forward slice. The result of backward slicing will be known as the backward slice. This is not a new idea. This already has been shown in the literature. There is not too much about slicing in functional programming setting literature, but there's a ICFP 2012 paper called Functional Programs that explain their work, and that paper introduced a language called TML, that is Transparent ML, which was a simple, purely functional programming language with all the most important features of purely functional languages, namely sum and products data types, and most importantly, higher order functions. And in the work I'm presenting today, we have taken TML and extended it to become ITML, that is Imperative Transparent ML, by adding references, loops and arrays, which once you have references are just simple extensions that piggyback on the implementation of references, and we've added exceptions. So in our new approach, you can, for example, write a program that looks like this. This program creates two references, puts them in a list, and maps a lambda over that list, and that lambda has some side effects. If you run that program, it will raise a division by 0 exception. And in our approach, you can slice that program to obtain an explanation why this happened. Okay, so you might have noticed in my example that the slicing criterion and the forward slice were identical. And the question is, does it have to always be the case? Well, it doesn't. It might be the case that there are some sort of data dependencies, and it is not possible to retain one value without retaining another, or discard one value without discarding another. So more generally, what will happen is we will say that the forward slice can be more defined than the slicing criterion, which intuitively means it contains at least as much information about the structure of the value as the slicing criterion. And we call this property consistency. Consistency by itself is not very useful. If I, for example, had a backward slicing algorithm that didn't introduce any holes at all and just reconstructed the whole program, then the result of forward slicing would be a value that doesn't contain any holes, and consistency would trivially always hold. So another property that we want from our slicing algorithm is known as minimality. And what this formula says is that given some slicing criterion v prime, we want the backward slice to be the least defined program, and this is the intersection part, that suffices to construct the value that is at least as defined as the slicing criterion, and this is the condition in the set comprehension. And to achieve that property, we will rely on something that is called a Galois connection. That is, we will construct backward and forward slicing functions as functions converging between two lattices. Let's look at a simple example. No side effects so far, just purely functional computations. I have an expression, a pair with components 1 plus 2 and 3 plus 4. And like I said, it is possible to replace sub-expressions of this expression with holes. And this creates a partial ordering relationship, which I have informally called less defined than or more defined than. And I can continue doing this. And by doing so, I have obtained a set, a finite set, that has a partial ordering relationship. And therefore I can say that partial expressions form a finite lattice. Having done that, I can start forward slicing these partial expressions. So forward slicing expression at the top is very simple. It's just normal evaluation. But what about this one? Here the second component is 3 plus whole. How do I forward slice that? That is, how do I evaluate that? Well, so in a purely functional setting, the intuition is that holes propagate. So if I have an operation where one argument is a hole, and I need to know that argument to compute the result, then the result is a hole. And similarly with all other partial expressions in this lattice. So partial values also form a finite lattice in the same way that partial expressions formed a finite lattice. Another observation, an important one, is that forward slicing function preserves meets. Quick reminder, meet in a lattice is the greatest lower bound, and what meet preservation means is that if I take two partial expressions, take the meet of those expressions and forward slice it, then this is the same as if I have taken those expressions, forward sliced them, and then taken meet of the result. Okay, let's put all these facts together. We know that partial expressions and partial values form finite lattices. We know that forward slicing is meet preserving, and we want backward slicing to be consistent and minimal with respect to forward slicing. And from mathematics, we know that if we have a forward slicing function that is meet preserving between two lattices, then there exists a backward slicing function that forms a Galois connection with the forward slicing function. Quick reminder, what is a Galois connection? If we have two sets, P and Q, each equipped with a partial order, and we have two functions, f that goes from P to Q, g that goes from Q to P, then f and g form a Galois connection, which is written with reversed turnstile. If and only if, when f of p is smaller than q, if and only if p is smaller than g of q, okay? And so what this means in our concrete setting, if we instantiate f and g, we have backward slicing function that goes from partial values to partial expressions, forward slicing function that goes from partial expression to partial values. And these two functions form a Galois connection when backward slicing, given slicing criterion, is smaller than a partial expression, if and only if forward slicing that partial expression is greater than the slicing criterion. Okay? Second conclusion that we can draw is that if we have forward and backward slicing functions that form a Galois connection, then backward slicing is consistent and minimal with respect to forward slicing, and these are the properties that we want. And final conclusion is that the choice of forward slicing function determines the backward slicing function. And I want to be very clear at this point. It doesn't mean that if I define a forward slicing function that I will get a backward slicing function for free. No, what it means is that if I define a forward slicing function, then firstly, I know that a backward slicing function that I'm looking for exists. Secondly, if I manage to find that backward slicing function and prove that it forms a Galois connection with my forward slicing function, then I will obtain the guarantee that my backward slicing function is minimal. And this is something I want for my solution to be practically usable. Okay, so I've shown you this simple example in purely functional setting. What happens if we add imperative features? So for example, what happens if we have side effects? We have, in this example, a reference store with references L1 equal to 1, L2 equal to 2. And we have a program that assigns 0 to L1 and then constructs a tuple from these two references. And if we evaluate that, we will get 0 and 2 in a tuple. So now, what happens if I throw away the reference assignment and replace it with a hole during forward slicing? So the evaluation rule for sequences says that we just evaluate the sequence by doing whatever side effects are in the first part of the sequence, then we discard it and we just return the second part of the sequence as the result. But if I try doing this naively, that is, if I discard the whole and just compute the result, I get a different result, and that is not correct. The reason for this is that in the presence of side effects, any whole can modify any reference in the store, and I have no information about that. So a safe thing to do would be to replace, well, since every whole can erase anything in the store, then every time we encounter a whole, let's just erase all of the store, and then my expression will evaluate to a pair of holes, which is correct but useless. What I really want to do is erase only those parts of the reference store that were actually erased by the parts of the program that I replaced with holes. Similar problem arises for in the presence of exceptions. Again, if I have a sequence with exception and it evaluates to an exception full, and I erase the first part of the sequence, I don't have enough information to recover the control flow. And I really want to be able to do something like this. So here's how we achieve that. We define an evaluation relation that says that given an initial environment rho and reference store mu1, expression E reduces to result R, either a normal value or an exception, produces a new reference store mu2, and there exists a trace T that witnesses those computations. Most importantly, trace T at this point records information about any exceptions being thrown or references being allocated or modified. We introduce a concept of annotated holes, where holes can now be annotated with information K, which tells us, which gives us information about the return type of this operation, that is, whether it returned a normal value or raised an exception. and it's annotated with L, that tells us, that gives us a list of references that were modified by those computations that the whole replaces. Having done that, we can define backward slicing like this. That is, backward slicing takes as input the slicing criteria, which is now some R prime and possibly a reference store mu2 prime. And it also takes a trace and returns new environment, reference, store, expression, and T. All of them partial, that is partial expression, partial trace. Partial traces now contain holes, annotated holes. It must, of course, be the case that our slicing criteria are smaller than the ones we've gotten from our computations. And it must be the case that the result we get back from backward slicing is smaller than the things we started with when we were doing our computations. And since partial traces now contain annotated holes, we can perform forward slicing in this way, and the results that we get have to be more defined, or at least as defined as the slicing criteria that we started with, but they can be less defined than the values we've gotten from evaluating the program. And so we can now forward slice these partial programs in a correct way. That is, we now have information that this hole here returns a normal value, and it erases the reference L1, and so we can evaluate correctly to a tuple that contains hole and integer 2. Similarly, now we have annotation that this hole raises an exception, so we have enough information that allows us to recover control flow information. And so we have developed a slicing framework that is based on Galois Connection that handles functional programs with references and exceptions. And the presentation was very high level. The paper will give you full details. Most importantly, it will give you precise rules for forward and backward slicing. There are proofs of correctness. That is, there are proofs that our definitions of forward and backward slicing indeed form a Galois connection. There are some more examples, more complicated ones than the ones I have shown you here. And there's also an implementation of backward slicing. That implementation is available on my GitHub account. Thank you.